Today we're going to take a look at section 2.7, and 2.7 has the title Implicit Differentiation. And what I'd like to start with on implicit differentiation is to kind of talk about what we've been doing. We hadn't given it a name yet, but the name for what we have been doing is called explicit differentiation. So what we have been doing is we've been able to take a derivative, and this almost makes it sound like we actually did something to achieve this, but all the derivatives pretty much that you've started with have started out saying y equals something, or f of x equals something. And that something, everything on the other side of the equation, is all in terms of x, or t. We've seen t used occasionally too. And so then we've taken the derivative explicitly. Okay? Y is on one side, x on the other. What we're going to see in this section is something called implicit differentiation. It means that either you cannot get the y and the x separated, or it just might be difficult to do so. Okay? So in general, what we're talking about is having y's and x's on the same side, either the left or the right, and working with them from that point. And in order to do that, what we basically do is we treat the x and the y both as variables. And then we employ all the derivative rules that we've been learning. Chain rule, product rule, quotient rule, power rules, sum and different rules, all the same rules. We're just treating the x and y as both having a variable status at the same time. So jot that down. All right, so the easiest way to show you how this works is to just show you a problem where we're going to use it. The first one we're going to take a look at looks like this. It's worth mentioning that we could solve this for y. There's only one y here. It is squared, but we could subtract the 37 to the other side. We could divide by the x squared, and we could take a square root, right? We could do all of those pieces. We could use then a chain rule because we'd have a square root. We could go through all of that, and we would get a solution, and that would be fine. But I'm going to start with this one simply because it's a nice, clean one to start with. That's really why. All right? So the way that we do this is we first recognize that the x squared and the y squared that are here, how are they joined? What operation joins them? Multiplication, which means that if we're talking about taking a derivative, what's the basic derivative we've got going on? There's a product rule, right? Because it's a product. Everybody good with that so far? The x squared and the y squared are multiplied. So we're going to use the product rule. The product rule says that I'm going to write down the first function. That's x squared, or the first component of the product, x squared. The next thing I need is I need the derivative of y squared. What's the derivative of y squared? 2y. Almost. That's what we would have done so far, right? Well, think about this with me for a moment. This is y squared. The problem is that this is y squared of some variable x. I mean, it's a function in terms of x, or at least potentially so. And so when we take the derivative of y squared, we have the 2y, but we actually have a chain rule. We have y as a function. So when we started out a function of y equals whatever, we took the derivative of y and we got y prime, right? Because the derivative of y is y prime, or dy dx, if you wanted to use the notation that looked like that. So when we take the derivative of y squared, we get 2y, y prime. Because the derivative of y itself is y prime. It actually lends itself better, I think, a little bit to recognizing it like this. Because if we were doing it from this perspective, and we talked about x squared, you could actually say this is 2x dx dx. And what would dx dx be? 1, right? That doesn't happen with dy dx. It's not 1, at least not generally speaking. So that dy dx, or the y prime, is part of the function. So the kicker is, anytime you see y and you take its derivative, you're going to have a component of it that's going to say y prime, because that's the derivative of y. It's y prime. Okay? Kind of like the derivative of x is simply 1. The derivative of y is y prime. So this piece over here then is 2y, y prime. It's a chain rule. That's really what you have there. You have a chain rule. You have something squared. So you're going to get 2 times the something and then the derivative of the something, which is the y prime part that's going on. Okay, that's half of it, product rule, right? So the other half of the product rule says I'm going to have addition. What's the derivative of the x squared? 2x. And then we write down y as it is, because, I'm sorry, y squared as it is, because that's the other component of the product rule. Derivative of 37, that's 0, so I've just got equals then. And then the derivative of 4x, 4. That is all the calculus that there is in the problem. But there's a little bit of algebra still left to do, right? What do we have to do to solve the question that's asked, to answer that question that's asked? Yeah, I need to separate the y prime. So I may not have originally had this as y equals, but the solution that I'm trying to find is what does y prime equal? So I'm going to take the problem and separate out what does y prime equal. So what I'm going to do that first? Right, so the piece that does not have a y prime in it needs to move. So this is going to be 4 minus 2x squared, 2xy squared, excuse me. Then what? Divide by the x squared 2y, and if you prefer, and I'll write it in the sort of a coefficient first, 2x squared y. It's the same thing, but we usually see the 2 written at the beginning. So we actually have the y prime on the left now. I can do one little simplification step on the right. Do you see what it is? Yeah. Every term has a 2 in it, right? This 4 has a factor of 2, this 2xy squared has a factor of 2, and this 2x squared y has a factor of 2. So we're going to reduce them all by dividing by 2. So this one divided by 2 is 2, this one divided by 2 is 1, and this one divided by 2 is a 1. So I end up with 2 minus xy squared over x squared y. Now notice the solution, this answer, is in terms of x and y on the right-hand side, isn't it? So it doesn't look the same as the answer would have been had I solved the original problem for y and done this explicitly. The answer looks different. It's equivalent, but it looks different, and this is the acceptable way that we would leave the answer written. Any questions on that one? Yes?
So you don't want us to write like dx dx?
You can't, no, the dx dx will never write, yeah. If you would prefer, instead of writing y prime, to write dy dx, then that's cool.
Okay.
That's,
I didn't know if you wanted us to like write, because that's how
and that's how the last calculus book that I taught would have done it too, and that's how I've mostly done it, I would say. This book tends to use the y prime notation, at least as far as I can tell as I've looked. So it doesn't really matter to me. If you're comfortable with dy dx, that works great. I like the dy dx and also a little bit better than the y prime because the y prime could be misconstrued as y to the 1. So if you're using the prime, make sure to remember that it's not a number 1. It's not bad, it's just it's easier to sort of miss in the process than the dy dx is. So, all right, let's go ahead and try another one. This one says we're going to find the derivative y prime of x implicitly, same directions. What do you notice the first chunk here to have, though? What's going to go on with this piece? That's a quotient rule, isn't it? All right, so let's see what you guys remember about the quotient rule. What do I do when I start the quotient rule? All right, I start with the denominator, right, which would be y here, times, would you have my?
Derivative of the
Which is? 1, yeah. So the derivative of x plus 3, which is 1. Next thing is subtraction. So what am I going to subtract? The top, right? That's part of it. So the top written as is, so that's x plus 3 times what? Y prime, because that's the derivative of the denominator. Very good. And all of that is the numerator of the quotient rule. What goes in the denominator? Y squared, because it's just the denominator squared. Excellent. Good job, guys. And then this is supposed to equal. Well, all right, what do we have now? What's the derivative of 4x? 4. And then the derivative of y squared? 2y, y prime. Very good. So that one's the piece that we actually saw in the last problem, very similar. There's something different about this problem. The primary difference, anyway, I should say, is that if you take a look at this one, I actually have two y primes in the problem, right? I didn't have that on the last problem. And the reason that happened primarily is because I have actually a y in more than one location. I have two y's in this problem. I have a y in a denominator and I have a y squared as well. So that's why that happened. That's going to mean that the problem solves a little bit differently. So what would you like to do first as we simplify this problem? How about instead of dividing by the y squared, we multiply it on both sides? Would that be okay?
Yeah, that's what I figured.
Oh, I thought you said divide. I'm sorry, I misheard. Yeah, if we multiply by that y squared, and I'll put this in parentheses over here on the right, we eliminate it from the denominator, right? So the y squareds here on the left cancel. On the top here, I'm going to go ahead and simplify what's on top here as well. So y times 1 is just y. And then I can distribute this y prime through here. So this is minus xy prime and minus 3y prime. Now I actually have 3y primes distinctly in the problem. It's not a big deal, but it is something to be aware of. On the right-hand side, I have to distribute as well, right? 4y squared plus 2y cubed y prime. Okay, is everybody good with that step? Okay, anytime you have more than one y prime in the problem, the next step is going to be collecting all of the y primes on one side and collecting everything else on the other side. And it doesn't really matter which side you go with. I'm going to move the y primes to the right because then they'll all be positive. I kind of like things to stay positive. That's what I tend to do. But it doesn't matter if you switch it the other direction. So I'm going to move the 4y squared to the left. So it's minus 4y squared. I already have that 2y cubed y prime. And I'm going to add the xy prime and the positive 3y prime all to the right. Is everybody good with that switch? Once you're to this point, what can you do on the right-hand side? Yes, we're going to factor. We're going to factor out that y prime. Very good. So I have a 2y cubed plus x plus 3. And what's the last step then? Divide. So we're going to end up with y prime equals the y minus 4y squared from the left over the 2y cubed plus x plus 3 that was originally on the right, or at least the last step of it was on the right. And then we're finished. Just real quickly, notice none of the terms all have a constant value that's the same. You know, none of them all have an x in it or a 2 in it like on the last problem. So we should sort of visually check that to make sure there's not any reducing, but there isn't on this one. We're done. Any questions on that one? You guys are quiet today. Let's try a third one. What's different about this one? There's a sign. What else is going on this one? We've got an x squared. What's inside a sign? An x and a y. There are two variables, and they are multiplied, which means you got a product rule inside of a chain rule. You got it, good Brooks. There, you got it. Okay, so we've got the sign here, and I tend to like to put parentheses in just to remind myself that there is an inside of this that is not just x. The fact that it's not just plain x means I've got a chain rule. And this chain rule actually has a product inside of it. So I'm going to have to do a product rule for that xy as well. All right, so let's start with the outside part, though, the sine part. What's the derivative of sine? Cosine. Good. You guys know that from last section, right? And we rewrite the inside just like it is. We never change the inside when we take the derivative of the outside. But after that, we need to take the derivative of the x times y. So what will the derivative of xy be? It'll start with x, and it'll be y prime.
stays the same.
It does because we're doing the product rule. Yeah, I know. Don't get confused in the process here. You can't do the prime of each of them individually, right? So we have a product rule. We have to take the original part for the x and rewrite it. And then we want the derivative of the y. So that's y prime. Plus what? 1 y. So the derivative of x is 1 and the derivative, and then the y piece stays the same. So 1y or just y if you prefer. All right, so that's the left-hand side. How about the right-hand side? Somebody mentioned we had an x squared. So what's the derivative of x squared? 2x. And then the minus 3 is 0. So we just have 2x on the right. Okay, everybody good? This one actually doesn't have too much going on with the cleanup, not as much as the last ones anyway. So as we're taking a look at this then, we're going to use the, well, let me write it this way. We're going to use distribution to rewrite these. As I use my distribution, I'm going to write the piece that, well, this piece right here, each of those pieces, I'm going to write them in front of the cosine just so that I don't think that I'm somehow going to be able to combine them with the xy, because I'm not. All right, so the first one we're going to have is that xy prime times that cosine. So I'm going to write it in front, x, y prime, cosine xy, plus, and then I have the 1y or y, so this would be y cosine of xy equals 2x. Remember, xy is actually an angle, right? It's an angle inside of cosine. It's worth noting on this one, and it was true on the last one as well, although this one's even worse. Solving this for y wouldn't be possible, at least not with the things we've worked with so far. We could solve this particular one for y, but if we did, you would have a inverse sign, right? The sign with the little -1 looks like an exponent, and you do not have any derivative rules for what happens for those yet. So you'd be stuck, okay? On the last one, this one you could have had done as well, but it would have been very complicated, and it would have involved using completing the square potentially and some other sort of messes going on, or maybe quadratic formula. Would not have been friendly. So unlike the first example where we could have solved it for y and worked through it, the last two, it's not practical to do so. All right? We only have one y prime, though, in the problem, yeah? So what would be my next step? Good. So I'm going to leave the xy prime cosine xy on the left, and I'm going to get 2x minus y cosine xy on the right. One more thing to do. What is it? Divide? What are we going to divide by?
X cosine xy.
Good. You got two of you guys saying it. X cosine of xy. So my final answer then will be y prime equals 2x minus y cosine xy over x cosine xy. What do we think? It's okay? All right. The next problem has some directions that are familiar to you at this point in time. They ask you to find the equation of the tangent line. So when we've been doing this before, we've been given an a value down here, haven't we? It says something like a equals 2. And that's an x coordinate, but it's an a value. This is actually a little friendlier because what do they actually give you? The x and the y. That's really nice. Now, if they didn't give you the x and the y, could you find the other one? Sure, you could do that. But on this particular problem set, when you get to your notes or into your homework, they're going to give you the x and the y. So that's really nice. Which means the only thing I actually need to do is get the slope. And we get the slope by doing the derivative. All right, so slope's the only thing we're going to have to find the equation of the tangent line. Notice if you've printed this off that your directions actually have a strike through on them. Who has printed copies of this today? Okay. If you don't have this printed off, I'm making mention of this because I'm actually changing a little bit of what the directions say that you have to do or could do. part of the directions in your book say if you have a CAS stands for Computer Algebra System, your calculator books would work on this. If you have a CAS that will graph implicit curves, you can sketch the curve and the tangent line when you're done. Most of you don't have that kind of a computer or calculator, and while you could have access to it online, that's great. The ability for your calculator to be able to do this is your ability to actually plug in an equation that's not in y equals form, right? The TI-84s that most of you use or TI-83s, that you have to put it in y equals form. You have to have it explicitly solved for y. So if you don't have a calculator that will actually allow you to put something in that looks like x cosine y equals 1 or whatever, you wouldn't be able to do that part of the problem. So I'm just striked it out. You don't have to show that piece on your work. So we're just going to find this equation and go from there. So we need to find the derivative, we said, right? Because we identified that this is x1, y1 in terms of plugging this into our point slope form of our equation. All right, so what's the derivative of x cosine y? What do you notice there? There is a product rule, very good. And we've got a chain rule because there's a y inside of the cosine. That's important to notice as well. All right, so we start with rewriting the x. So what's the derivative of cosine of y? Right, I'm going to put the negative in front of the x, and then I'll put the sign next. With the interior, that is the angle, the same. But then I need the derivative of the angle, and what's the derivative of this angle? Y prime. The derivative of y is y prime. Oops. The other half of this is the other half of the product rule, right? So I've got addition. And what's my other piece going to look like? 1 times the cosine of y. Perfect. And what will all of this equal? 0. Yeah, but remember to take the derivative of the 1, so we're going to get a 0 on the right. It's an easy thing to overlook, that simple one, in the midst of doing everything so much more complicated. This isn't bad, and to be honest, we have all the pieces that we need. We don't have to simplify this. We don't have to solve it for y prime directly. We don't really care what y prime equals. We care what y prime equals at this xy coordinate. So I'm going to put those x and y in. Okay? So x is 2, so this is negative 2. Sine of pi over 3 times y prime, which is what we're looking for. We'll solve for it in the end. We'll solve for it with specific values plugged in. And then I have the cosine of pi over 3. And just for fun, let me go ahead and move this cosine to the other side, because it'll be negative cosine then on the right. We're going to have to do that eventually anyway, so I'll just do it in this step. So if you don't remember, a unit circle might help you. Your calculator might be a good reference tool, but we need to find the sine and the cosine of pi thirds. Do you remember what they are? One of them is square root 3 over 2. Do you remember which one? The sine value. That's correct. So this is square root 3 over 2. Do you remember what the other one is, Jamie? It is. Very good. All right, so the cosine value is 1/2. The sine value is square root 3 over 2. They're both negative, so we could get rid of the negatives, right? Because we could multiply them both by -1. What else do you see simplify over here? Those two 2's. So I'm left with the square root of 3 that then needs to move to the right-hand side. So what will the right-hand side become? That's exactly right. So we can multiply both sides by 1 over square root 3, right? That's not rationalized. Do you remember how to rationalize that? Yep. So square root of 3 on top. What do we have on bottom? 6. So my slope is square root 3 over 6. You may not like this slope. That's okay. That is the slope. We're not going to abbreviate it or approximate it in any way. This would be correct. So now I can actually find the equation of my line. So I'm going to do y minus the y1 value, which is pi thirds, equals the slope, which is the square root 3 over 6, times x minus the x value, which is 2. And we're going to solve this for y. So One of those steps is going to be to distribute that square root 3 over 6. The other one is going to be add the pi thirds. So this would be square root 3 over 6x. What are you going to get when you multiply square root 3 over 6 times negative 2? It'll be negative, but what else do you get? Right, root 3 over 3. And then I'm adding that pi thirds over here on the right-hand side. You can leave it right here if you'd like. If you were checking the back or if you were comparing with someone else, another way you might see it written would be to go ahead and combine those last two because they're both constants and they have the same denominator. So we could actually write this as positive. I'm going to put the pi minus the square root of 3 just so that the subtraction occurs in the middle of it. But if you put negative square root of 3 plus pi, that'd be fine as well. So this would be another way of viewing that particular equation. Either of those would be fine. Any questions on that one?
Yeah,
Yes.
I heard you say it, but I didn't see it. How did you make the cosine of pi over 3, or the negative cosine of pi over 3 positive 1/2?
This piece over here,
Yeah.
turning into positive 1/2.
Yeah.
I just noticed that I have a negative on both sides,
Okay.
so I made them both positive.
Okay.
So, I mean, if we didn't do it there, we would have done it eventually. Yep. Any other questions on this one? Okay. The next question that we're going to encounter is actually quite different than we've seen before. We haven't done anything with this particular question till now. It says, find the locations of all horizontal and vertical tangent lines. So we need to pause for a moment and consider what in the world we're looking for if we're trying to find horizontal or vertical tangent lines. So I want you sort of in your mind to picture what does a horizontal line look like. Got it in your head? Okay, describe for me what you're seeing. Lines are always straight. Use another word, Brooks. Horizontal, but what does it look like? It's flat, right? It looks flat, right? It's like the horizon, like on the sun, right? The horizon. Right, so it's a flat line like this. What can you tell me about a flat line like that? The slope is what? Slope is 0, yeah. So when we're looking for a horizontal line, we're looking for something that has a slope equal to 0. Now, that's the deal. All right, so let's do the same thing now to think about with vertical lines. Can you picture a vertical line? Okay. What can you tell me about that line? How does it look? Besides straight. How's it go? Up and down, like a wall, right? Or like a pole, like a flagpole, up and down. So it goes up and down. What can you tell me about the slope on that? It's undefined. So this one has a slope that's undefined. So if you take a look at both of these, we can talk about horizontal and vertical lines based on their slopes, right? And how do we find slopes for curves? We take derivatives. So that's where we're going to start. We're going to start with this particular function, and we're going to take a derivative. And this one's not near as bad as the ones we've been dealing with, because I don't see any product rules, do you? Or quotient rules. Whew, that's nice. All right, so what is the derivative of the x squared? 2x. How about y squared? 2y, y prime. That's the third time we've done that one, isn't it? How about the derivative of the negative 3y? Negative 3. And what does this equal? 0. All right, everybody good with that? All right. Looks great. And in order to talk about the slope, we actually have to be able to say what the slope equals. So I'm going to solve this for y prime. So two pieces of this don't have a y in it. So I can add the 3 to the right, and I can subtract the 2x. Does that look good? And then I can do what? Divide by 2y. All right, so I have y prime equals 3 minus 2x over 2y. There are two things I'm supposed to be finding. I feel like, oh, we missed something. We need to come back to here. I didn't notice it either as we went through. What's the derivative of 3y? Maybe somebody said it and I just didn't hear it.
-3
Y prime. Sorry, I overlooked it too. That's going to change our answer. It's a good thing we caught it. I actually have two y primes now, so those two will stay. The 2x can move, though. So I've got the 2y y prime minus 3y prime equals negative 2x. Then what would I do? Take out the y prime. Very good. So what does that leave me with? 2y minus the 3. And then what will y prime be? Perfect. You guys got it. Good. All right. That looks better. Well, it looks correct anyway. I don't know about better, but it looks correct. All right. So we've got all our pieces there. Now that's good. Let's go back up to what we were looking for. We were looking for, and we'll do it one at a time. We'll do the horizontal one first. The first thing we're looking for is for a horizontal line where a slope is 0. So this is my slope. My slope is negative 2x over 2y minus 3. How in the world am I going to get that expression? So if I'm ready to do number 1. How am I going to get this expression to be equal to 0? What actually has to happen to make that work? Very good. The numerator would have to be 0, right? Because if the numerator is 0, I get 0 over something else. As long as the something else isn't 0, then I would get an answer of 0. So when will this numerator be equal to 0? When x is equal to 0. But we want to find a location, and a location in two-dimensional space means what am I looking for? An x and a y. So I have found one of those pieces, namely the x. Now I need to find the y. How do I find the corresponding y? Very good. I plug it into the original equation. So my original equation started out up here at the very top right here. And I want to let x equal to 0 now, right? So this would be 0 squared plus y squared minus 3y. And is it okay with you guys if I move this negative 4 to the left? Okay. Why might I want to do that? So I can factor. Anytime I'm dealing with a quadratic, that is an x squared, with a linear factor, which it does have that negative 3y in the middle, I would need to factor. So how will this factor? Minus 4 and plus 1. Very good. Which means, what does y equal? 4 and negative 1. Be sure to answer the question asked. The question was, what is the location of the horizontal tangent line? So what are my locations for my horizontal tangent lines? Perfect. So there's two answers, well, not two answers. Well, there are two answers to this part of it. I've got more answers in a minute. But the answer to the horizontal tangent lines is that I have two locations. One location is at 0, 4. The other location is 0, negative 1. Might be worth noting now that you do know for sure you do not have a function on this graph. You don't have a function because I have x values that match, x equals 0, and I have two corresponding y values. So it actually fails to pass the vertical line test if we were to try to graph this points. All right, slope undefined. So how in the world do I take y prime equal to negative 2x over 2y minus 3? How do I make this undefined? Good. This one is equivalent to letting my denominator equal 0. So if my denominator equals 0, what would y equal? 3 halves. So add the 3 to the right, and then divide by 2. Again, that's only the x value, right? So, I'm sorry, that's only the y value. I said it wrong. That's only the y value. It's only 1/2 of the answer, correct? So I have to find the corresponding other piece, which is the x value. Yes, thank you. So I'm supposed to be finding x squared plus, this is my y value, so this is y squared, minus 3 times y equals 4. All right, so x squared plus what? 9 halves minus what? Three times 3 halves is, we do 9/4. There's my 9/2 that I was hearing you guys say. Yeah, and then equals 4. Thank you. Catch my typos today. You guys are doing great. All right, so how are we going to combine the 9/4 and the 9/2? Common denominator, which will be a 4. So this 9 will turn into a 18. So what do I get when I have 9/4 minus 18/4? Negative 9/4. Oops, equals my 4. Then what? I think we want to add, right? X squared equals 4 plus the 9/4. How could I write 4 differently? 16 over 4, because it's equivalent to 4 over 1 to start with, right? If I add those together, what do I get? 25 over 4. And then what happens? Square root. So what does x equal? You guys caught it. Very good. Plus or minus the 5/2, right? 2 answers for x. All right, so answers to the question, where is the slope, or where is the tangent line undefined? Five halves, 3/2, and negative 5/2, 3/2. And I labeled this as undefined. I guess the original problem actually labeled it as a vertical tangent line. Same thing. All right, so we've got a vertical tangent line at those two particular points. Any questions on that one? We have one more problem. We are asked on this problem to find a second derivative, y double prime. How do we start? With the first derivative, right? The starting point of all of these problems is find a derivative. So as we're taking a first derivative, what is the derivative of x to the 2/3? Negative what? 1/3. You're right. Negative 1/3. Everybody get that okay? It would be the 2/3 minus 1, so 1/3. How about the derivative of y to the 2/3? What do we think? It starts out the same, 2/3. Y to the negative 1/3. Starts out the same, yeah. None of that's getting different. Times the y prime. That part's different. And then this equals 0. Okay, that's all the calculus in finding the first derivative. However, in order to find the second derivative cleanly, we want to solve for what y prime equals. We need to get this to say y prime equals something. That'll be much easier for us to solve for. And we have some options here on how to deal with this. So obviously, we need to move the 2/3 to the other 2/3 x to the 1/3 to the other side. And then we're going to need to do some division or some multiplication or something. We can actually deal with the fact that we've got negative exponents and turn them into positive exponents as well. We could do all that. The cleaner that we can get the first derivative, the easier the second derivative is to take. That's kind of your rule of thumb, and that's the kicker here. Not because we have to get it cleaned, but because it's going to make it easier for our life later if we do. So the first thing that we'll do is we'll move that 2/3 to the other side. In fact, well, I'll save that for another step. So my 2/3 y to the negative 1/3 and the y prime are going to stay. And I'm moving the 2/3 x to the negative 1/3 to the right. All right, there's one step that's really easy to take care of right away. What is it? Cancel out the 2/3, right? We've got 2/3 on both sides. If you don't like the phrase cancel them out, which isn't probably the best mathematical phrase that anybody ever invented, we're actually multiplying by the reciprocal, right? If you multiply both sides by 3/2, they go away. So I actually end up with y to the negative 1/3 y prime equals negative x to the negative 1/3. And then based on what we've done before, you guys know that what do we want to do with this piece? Divide it, right? Okay, so this can be written, one way it can be written is y prime equals negative x to the negative 1/3 over y to the negative 1/3. I'm not a super big fan of the negative exponents because they can be changed to positive exponents. What would I do to change both of these to positive exponents? Flip them. That's kind of nice. The other thing about that that's kind of nice is that I can also write them, well, let me do that in another step. I'm trying to get ahead of myself, I'm sorry. So this is y to the 1/3 over x to the 1/3. And we can deal with it like that. We could use a quotient rule, but even as we use our quotient rule, we're going to have some chain rule stuffs involved, right? Because we've got that y to the 1/3 there. So another option that we could write this as, that doesn't look very good, would be to write this like this. It doesn't make any difference. It's just easier to work the problem out, depending on your perspective, I guess, maybe, in one of these two ways. You have a couple options anyway. So I think we're ready to do the second derivative, yeah? All right, so my first derivative started like that. All right, so my second derivative then, I've got the negative. What do I do next? Chain rule first, because I've got something on the outside of it, right? So the 1/3, at least using this particular view of it, would be the chain rule. So the 1/3 would come down in front, right? We would rewrite what's inside. And what is the new exponent going to be? Negative 2/3. Very good. And then we would use the quotient rule for the inside part. So that we're going to take the derivative now of the y over x. So what will that look like?
X
Good.
minus y.
Y times 1.
Over x.
Excellent. I like the chain rule on this one because the inside derivative is really clean, right? X over y is not too difficult to do the inside chain rule for that. It would have been much more complicated to do, not chain rule, but the quotient rule. It would have been much more complicated to do the quotient rule with a y to the 1/3 next to the 1/3. It's kind of what I was avoiding. I was having so many exponents everywhere. I can avoid a lot of those exponents if I do it as a chain rule. All right, so a few things to notice here. The negative 1/3 I'm going to leave alone. I can actually flip this fraction, y over x to the negative 2/3 again, right? If I flip it, I get a positive 2/3. So I can extend this. I can make this an x to the 2/3 on top and a y to the 2/3 on bottom. Is everybody okay with that piece? Are we?
Wait, can you say that again? What you did?
The negative 2/3, I flipped the y and the x, so I put x over y. So x is on top now and y is on bottom, so that makes it a positive 2/3. And then I applied the 2/3 to the top and to the bottom individually. This piece over here is going to be much the same as it's already been, x to the, or xy prime minus y over x squared. Let me write it a little bit differently. That is in combination with the fraction I already have. This is x squared, and then this is x y prime minus y. Kind of combining it into one fraction. There's something that we have to do on this problem that we haven't seen before. What we have to do is, you see where it has that y prime in there? We know what y prime is. We have to plug it into that part. Before we do that, though, I'd kind of like to clean up my x to the 2/3 on top and my x squared on bottom. Is that okay with you guys? One way to think about that is to simply write this as x to the 2/3 back on bottom as negative 2/3 to add them together. So that on top now, there's a negative out in front. Do you see that negative out here in front? I'm going to distribute that through the numerator, so this is now negative x y prime plus y. My denominator is 3. I have y to the 2/3. And what do I have x? X to the 2 minus 2/3. What's 2 minus 2/3? That is 4/3. But yeah, we have to substitute in what that y prime equals. So the y prime here is actually equal to, and I'll use the expression we had before, which was the negative y to the 1/3 over x to the 1/3. Plus the y. We're really close to being done. If you guys will bear with me for just one more minute, we'll be done with the problem so that we'll be finished with this section. This x and this x to the 1/3, those simplify, right? You guys with me? The x that's out in front and the x to the 1/3 that's in the denominator of the numerator, those simplify. So this becomes negative x to the 2/3, because basically we have the number 1 minus the 1/3. That doesn't look like a third. 2/3. Y to the 1/3 plus y over 3y to the 1/3. No, it's not 1/3, that's 2/3. And x to the 4/3. There's one thing we can do to simplify, and then we're done. Does anybody see it? What can be simplified? There's a y in every term. They have different exponents, but there is a y in every term. I can, in essence, take each one of these y's and take out the smallest y that they all have in common. The smallest y they all have in common is actually what? Y to the 1/3. So the equivalent, what I'm doing is I'm going to divide by y to the 1/3. If we do that, we get the negative x to the 2/3, standing all by itself. This second piece of the numerator, the y divided by the 1/3, would be y to the 2/3, because you have 1 minus 1/3. And then, we were missing a negative. I'll fix it in a second. We have a 3, and then we have y to the 1/3 in the denominator, because we had 2/3 minus the 1/3, and then x to the 4/3. There was a sign back here that I didn't get put in. This is a negative back here at the very bottom of the screen. Over here, I'll put it in red now. That one was a negative, which means that the sign here at the beginning should have been a positive. That's the only piece that's different. So x to the 2/3 plus y to the 2/3 over 3y to the 1/3, x to the 4/3. Second derivatives are complicated, right? They are, because we have to do this substitution step with y prime back in. All right.